I think we can go ahead and get started. Good morning, good afternoon, everyone. Welcome to Africa Calls Histology. My name is Ken Landgraf. I'm Executive Director of ASCP's Center for Global Health. And we are thrilled to be joined today by Rory Pilgrim, Google Research Product Manager, who's interested in medical imaging. So over to you. Just some housekeeping. If you have questions, technical issues, please put them in the chat. And if you have questions for the presenter, please use the Q&A feature. So over to you, Roy.
Fantastic. Thanks so much for your time, and hi everyone. Hope you're doing well. As Ken mentioned, I'm a product manager at Google Research, and at Google Research we've got a sort of relatively mature program of doing work in digital pathology AI. So we've published a number of papers, and in the last year or so, we've started releasing some of that work for the broader research community to play with and to build on. And so today I'll talk about two efforts we have in that. The first is an augmented reality microscope that we call ARM, which is something we published on a few years ago. And we just open sourced the software that powers ARM last year. So that's available for people to play with if they want to and to see if that's something of interest. And the second tool that we just released in the last few weeks is a pathology, a whole slide imaging pathology tool for AI, which we call Path Foundation. And this allows you to build AI solutions using whole slide images. And I'll give you a bit of a demo of that today. But I'll start with the ARM project, and then I'll talk more about the Path Foundations, if that's all right. So we started thinking about the issue with the digital scanning and digital pathology way back in 2018. And one thing we were interested in doing is thinking about how we can offer a solution that may not require you to invest in a whole slide digital scanner. Because at a point in time, and I still runs today, that's quite an expensive endeavor. And so we thought about, can we use the existing microscope and add a camera to that, so retrofit on an existing microscope, and then run AI live on that. So it's an augmented reality experience where the AI is making predictions of the camera from the slides. So the pathologist is just using that same workflow, but they have this projection of an AI image. And this is something we've done, and we published on it a while ago. Let me just see if I can share my screen here. Here we go. So we published this paper back in 2019 describing what this looks like. And you can see here what this looks like to the pathologist. And I'll just zoom in here so you can see that a little better. So this is the general microscope. And you can see the slide here. What we're doing is we're sending the image live to a GPU that's actually on site there. And that's running an algorithm that we've provided for this purpose. And then what it's doing is actually projecting that region of interest back onto the slide so the viewer can see this green outline to see something of interest there. So this is work we did with our friends Synoptic. And as you can see, this is just a sort of standard microscope that we've done this for. So we've done some work and done some trials live in the US. And there was a lot of positive feedback from pathologists there who were using this, and it helped them sort of identify regions of interest and just scan around and actually see things more quickly. It's not a guarantee, of course, that it's accurate, but it is helpful in terms of speeding up that workflow. And so last year, what we did is actually made the software that powers this available. So there's obviously some hardware that needs to be purchased, but the software is available. And so if people are interested in experimenting with this, we have both the software that powers the way the model sends the images to the GPU and runs the AI model, as well as the models themselves. Those are available on GitHub, and you can just sign up and use them today if you're interested. So that's something that's available today. I maybe just pause there and see if there's any questions about. We call this ARM, augmented reality microscope, but the ARM project and what it can do. Maybe before I stop for questions, I'll just give you a bit more background of the models that we do have available. So we have 4 models available. One is for breast cancer metastasis. We have a prostate cancer model, mitotic count model, and then a cervical dysplasia model as well. So 4 models that are available off the shelf. These are only licensed to be used for research, but as people give us feedback, we're open to thinking about how we might be able to enable more grand uses of those algorithms. I'll just pause there and see if there's any questions from the audience.
Nothing has come in yet.
No worries. So what I can do at the end of this is send the details for sign up if people are interested to see these things at work. We have a video that I can play now if we have time. Actually outlines how this works. I haven't tried to run a video through Zoom before, so I'm just worried about the audio not working. But maybe I'll sort of say that for the end if there's interest and we have time, and I'll move to the Path Foundation model. How does that sound, Ken?
That sounds great.
Okay, wonderful. And so ARM is a service that is kind of a platform that if you use the software, you can take the ARM models, you can add other models if you wanted to, and run them on that device. Path Foundations is a little different. It's more of a machine learning toolkit that allows anybody to build models that they're interested in for their use cases. And so it's not a specific model like breast cancer or prostate cancer. It's more of a tool, a framework. And the way it works is that it is a embeddings model. And what that means is that if you send this tool a patch from a whole slide image, a H&E slide, it is able to understand the core features ensconced in that patch and then produce a very structured piece of data that we call an embeddings. This is just a vector. It's a set number of numbers. And that can be used by a subsequent model to actually understand key features. So it still requires you to provide some labels. But the advantage of this approach is that when you want to build a model, a lot of the learning is already done. So rather than requiring thousands and thousands of labeled patches to build, say, a prostate cancer model or a mitotic cancer model, you may only need a few hundred. And so it's a hugely reduced number of data compared to before. And this is general across tasks. So because it's trained within H&E domain, you don't need to have additional, you don't need to have the thousands of patches that we've had before. So the model is doing a lot of the work for you, but there's still a little bit of work for you to do. And at the end, you have a model that works for whatever task you're curious in the H&E sphere. So we did publish a paper on this last year outlining this technique and how effective it was for existing tasks that we had. And we've just released this for access, and I'll just show you what this looks like here. There's an access form that I can link to at the end of this. But this is an example notebook. I'm not going to go through all the code here, but I'll just show you the results. I think that's interesting. So what we've done here is we've generated 500, we've taken 500 patches, and I'll show what those look like in a second. And they're labeled for tumor and no tumor. We're doing a very simple thing today. It's just tumor, no tumor on tissue. And we take these patches and we actually just train a very simple linear classifier. So linear classifier is kind of like a sum product. The dimensions are 384 numbers. And what we have to do is take the 384 numbers and work out what combination best represents a tumor. And if you think about this, this is a lot simpler problem than taking a say 512 by 512 pixels. That's a huge amount of data there compared to 384 numbers, much simpler problem to solve. And as a result, we need less data to do that. So in this example, like I said, 500 patches, 250 positive, 250 negative, and then we evaluate this on a set of 100, 50 positive, 50 negative, and we see what our performance is. So I'm not going to go through all the code here, but I'll skip to the answer here, which is the performance on this this evaluation set of 100. And we've actually got an AUC, for those who understand AUC, it's a receiver operator curve, area under that curve of 0.99 in this example. So that's a very high classification performance, and it means we're more or less getting the vast majority of cases right on those labels. So just visualize, I know lots of pathologists in the audience, so probably not interested in the curves, actually want to see the slides, but this is an example here of all of the 100 examples there and the scores, and then the tumor prediction and the ground truth here. So ground truth 1 means tumor is true, and if we're predicting true, then we've got that right. So that's a true positive there. And you can see at the bottom here, these are the ones that were not tumor, and they have low scores, so corresponding to the fact that the model is understanding that pattern. So for folks who are interested, here's actually what it looks like. So I'm visualizing a few of the true positives and the false negatives and the like here. Let me just rerun this because I put the label wrong. It's happening all live. So I've just pulled out, I think, 10 of these, and you can see this particular patch had a score of 0.6, and we got it right. So we're basically saying that anything above 0.65 is a true positive. Anything below that is a negative. So 0.74 there, 0.76. So you can see these patches are actually working in actuality. So that's all the true positives. Now we do have some false positives. So there's some things that are scored high that from our labels we're saying is not tumor. So this is one of these. This is another. There's only actually 2 in the whole data set because we have such a good performance. But like I said, it's not a perfect model. And we also have a few false negatives. So this is where we said that there was no tumor, and in fact there was. So this one has quite a low score, 0.13, and this has a score of 0.35, for example. So this collab is actually going to be available for people to run and play around with and just see themselves. This is all on Chameleon data set, so it's public data. You can test it out and actually train your own model and see what the performance is for you. But more excitingly for us is this is an actual API that's live, so you don't have to use our test set. You can adapt to fit patches that you have, and we've got lots of code to help you do that. So if you have whole slide images with interesting features and you want to make a prediction that's not tumor versus no tumor, you're more than able to do that with this API, actually run that, train a model, and then see how it works on how to data set. So to give you an example, to get this kind of performance in the past, we would need tens of thousands of labeled patches. We've done it today with just 500. So that's the power of this foundation model. And we're really excited to see, as people get access to this, what applications they want to build for problems where AI can help them in the day-to-day of life using data they've curated themselves, because the scale you need is actually much lower than before. So I've been talking a while. I'll pause there and just see if there's any questions about this. Once again, the signups and the resource I can link through so they can be sent out after the session.
I don't see any questions yet from the audience, but could you maybe talk a little bit more about linear classifiers and other types of classifiers in machine learning, and how we might build on this to not just tumor, no tumor, but actually specifying a type of tumor, for example?
Yeah, of course. So a linear classifier, if you think about there's 384 numbers, right? And so when we have a linear classifier, we assign a weight to each of those numbers. So we'll say this particular position 0, right, of the 384 positions, this one we think is really important. So maybe we give that a high weight and say if this number comes out high, we think that's very correlated with whatever thing we're finding, in this case, tumor. And then say feature number 5, we think actually if this is high, it's very uncorrelated. And so that may have a negative weight. So that might be a negative 0.8 or something like that. And therefore we actually penalize the score if it has features in that area. And what we do is we train a model that actually learns those weights. So it's just a single weight per feature there. So 384 numbers essentially. And then whenever we see a new embedding, we say, I'm just going to multiply each of my features, my 384 features, by the corresponding weight, add them all together, and that's my score. And that's the score you saw beforehand. So that's how we actually calculate these scores here. So it's like I said, it's a very simple model because there's only 384 parameters in this model. And from there, we have a very simple equation for, once I've got an embedding, of course, I can then quickly understand, is this a high score or a low score, and then therefore is it likely to be tumor or not tumor? Now, when it comes to using this to do more than just tumor, no tumor, it's important to understand, and I know I'm sort of pointing at code here, which is a little bit abstract sometimes, but the way that we've done this is just an example, but you can collect 500 examples here, and you can label them totally differently. So we had 500 examples, 250 tumor, 250 no tumor. I mean, it learned that linear model that I mentioned before with the 384 parameters for that particular task. But you can train a linear model for any task that you have, as long as you have some examples to learn those weights from. So if you had, say, prostate cancer as an example, you might collect a few hundred positives, a few hundred tissue negatives, and then learn from there a different linear probe using the same embeddings to classify prostate cancer. But you don't have to just do cancer stuff. You can do, is there tissue in this patch? That might be something interesting for you. You maybe want to classify what kind of tissue type it is. Is it prostate tissue, cervical tissue, lung tissue? That might be interesting. People have been interested in looking at more operational applications. So when they do whole slide imaging, occasionally you have low quality images. And that's a problem because you don't know necessarily at the time, and then that's been scanned, and you have to go back and actually fix it. But some of our collaborators are interested in actually just running this model on that to see, is there a high quality focus on this image? And if it's not, flagging that at the time of scanning so that they can go back and fix that and rescan it as required. So the range of potential applications is very large. It can be really clinical, like the cancer stuff, but it can also be quite banal, like is this a high quality image, or is this a lung tissue, for example? Those kind of things. It really depends on what is going to optimize your workflow. And what's really powerful about this is that you can build all those applications just from this single foundational model with minimal data. Ken, any questions on that? Does that all make sense?
No, that was excellent description or answer. Thank you.
Awesome.
I'm here now. Can you guys hear me?
Yep.
Yeah.
Yes.
Hi, Rory. How are you?
I'm good, thanks. Dan. How you doing?
Yeah, apologies. My Zoom needed to update, and then anyway, long story. I'm finally on.
No worries. That's why I always use Google Meet.
Yeah. It was a pain.
No, I'm just joking. Yeah. So we've gone through both models here, and so
Okay.
we've had a bit of an overview. Sort of just waiting for questions or any comments from what we've presented there. There's a video that I can share out and maybe just send on the arm that sort of outlines how this can work. But yeah, I guess I'd leave it to you and Ken how you want to take the session from here.
Right. I mean, we have some participants who I'm sure there were more when you were doing the demo that may or may not have had questions. The other thing is that, we're recording this. So typically, once the session is over, we will send it out. And we often get more questions then, especially when people have time to, go look at the tool or try to play with it on their own. That was my expectation for this anyway, is that probably there'll be a lot more follow-up questions than there were questions inside of the session. So yeah, so I think that's likely where we're headed with that.
Absolutely, no problem whatsoever. I've got the video here. Is it worth me trying to share this and just see if that plays? It's
yeah,
just
let's try it. We have plenty of time, so let's try that.
Okay, and like I said, I'm not experienced with trying to pipe video through Zoom, so just bear with me and let me know if it's working.
Okay.
There's no cancer treated without understanding what the pathology is.
The tissue slides that pathologists use to diagnose cancer contain a vast amount of information. It's very time-consuming, very fatiguing.
Every cell needs to be examined. Sometimes cancer is very difficult to recognize.
We had the idea for the Microscope project about a year ago. It brings augmented reality into an existing microscope to detect cancers in real time. We're bringing AI directly to the user and meeting them where they are right now.
I think this is going to enable almost all pathologists to have access to machine learning.
Just a few weeks ago, we got it working end-to-end.
It has a camera, so it's seeing the same thing I'm seeing. Information is being fed into a computer, which is doing billions of calculations and telling me that's the tumor, that's not the tumor.
Right now, it detects breast cancer and prostate cancer, but it could also work on any other cancer type that we train models for. The knowledge that you're getting when the microscope points out cancer to you is the knowledge of many pathologists who contributed to training the machine learning model.
We had a team of pathologists that went through thousands of images, teaching the computer what cancer cells look like.
I think it has been very effective at locating areas of concern. It's like getting a second opinion.
It's going to make the doctors much quicker, they're going to make them better, which is going to overall benefit the patient.
The mission is to increase the accuracy and availability of cancer diagnosis and save people's lives. I can hardly think of anything that's more motivating.
Yeah. If that's the only problem, that's the only problem with sharing a YouTube video, that'll immediately start sharing the next YouTube video. So Rory, for that video, that's one tool. That's the AI that looks specifically at breast and prostate cancer. But you were demonstrating, and I apologize for being late, you were demonstrating two different tools. Which of the tools are you demonstrating that's related to that video? Oh, we can't hear you, Rory. I can't hear you. But you're not muted. That's really weird. There we go.
Can you hear me now? Yeah.
Yeah.
Sorry. Zoom switched over my microscreen there. But I was just saying that that was the ARM, the augmented reality microscope. So that's sort of software that powers that has now been open sourced, and we've actually added 2 more models to that. So in that video, we were talking about breast and prostate. We've got mitotic count there. So this is just detecting mitosis within tissue specimens, and cervical dysplasia as well. So those are 2 other models that are available, and that plus the software that actually drives the that setup is available today. You obviously have the microscope and the GPU has to be provided, but there's instructions on how to do that if people are interested. They can also just run the models in isolation just to see how they work. The tool I was demonstrating before is the more recent tool, which is Path Foundation, which is not a hardware package. It's more of a software package. So it sort of assumes that you can get digital pathology images to it, and then it can produce these embeddings that make the process of building models much, much more efficient, and mean that you can sort of circle tens, maybe low hundreds of images and get a really high performing model on whatever task that you're interested in within the H&E space.
Right. And that was actually my question that I was to make sure you didn't already answer it for the rest of the group. So with the Google AI video that you just shared and the breast and the prostate module, you said you fed it thousands of images. Do you know roughly how many images per cancer it took to train it? And what is that requirement now for this other tool?
Yeah, so it's now in the hundreds kind of thing. And the trick with this is we talk about patches when we train the model, it's trained on a patch level basis. So not the whole slide image, but a very small patch. And I just share what the size of those patches tend to look like. So this kind of size of image here. So this is obviously a very small patch. It's a 40x, I think. Versus like there's thousands of those in a whole slide image, of course. So this is a very small portion of that. So we might have thousands of slides in these original models. This is the ARM original models, but millions and millions of patches because each slide has so many there. So there's a variance across patients and tissue specimens, but also within the tissue, there's just a huge amount of information that we're feeding into the model to learn about which areas are of interest. And what we've done in this demo is just train a tumor, no tumor with a total of 500 patches. Now you can actually, if you want to play with this, you can actually use less and see what happens there. I'm not going to try and do that because when I code live, it's going to be a disaster. But it's very easy for you to just actually reduce the number of patches we're pulling in here and just see what's the performance there. You can actually run that experiment yourself here. So like we pull in 500 to give you 500 in this demo, but when you train this, you could actually reduce the amount of training and just like cut it in half, or cut it as low as you want, just to see how it goes. Then we evaluate that on another 100 patches, and those are fresh. We haven't, the model's never seen those before, and we calculate this ROC curve from that. So I wouldn't change that. I'd keep that 100. That's a pretty good balance, and that's 50 positive, 50 negative in this case. And that just gives you a sense for how well it's performing on unseen data. And so that's kind of gives you a sense for what this looks like. In the paper we published, we actually demonstrated what this looks like and how it performs across a number of tasks, including prostate and breast cancer. And we're talking about a couple of orders, or even 3 orders of magnitude, like sort of 1,000 times less data required with the foundation model than before.
And so your patches that you showed look like they're about maybe 15 to 25 cells. Can you make smaller patches? Can you get down to the individual cell level as a patch, or is that not the point of the approach?
So this model has been optimized for around, I think, 10x to 40x, that kind of magnification, and then the patch size is fixed. So this is kind of the size the patch it expects. You can obviously imagine there's an alternative, an expansion of this work where we look at higher magnifications at the cellular level, but that's, you could obviously try it. That's the beauty of what we're doing. You could feed it patches like that and see what happens. We haven't tested it on that though, so I'm not sure what performance would look like. In our other work, we have a number of foundation models. People have sort of tested them on things, or said, well, we didn't actually train it to do that, and found it performs really well. And an example of that is in our chest X-ray foundation model, which is similar to this. This is on adult chest X-rays, and we had a collaborator work on abdominal neonatal X-rays, and had a really good performance out of that. So even though it wasn't something we'd necessarily expected to work on, it did actually do quite a good job. So if you're interested and you have the patches available, you can throw them in the model, and it's not very hard to see if it actually learns something from that.
We have a question from our dear friend and colleague George in Ethiopia. How specific and sensitive is the AI able to diagnose or detect the positive cases? Does it differ from organ to organ or from case to case?
Great question. So what we did here is, this is a little bit of code where, so this is an AUC curve, and it's giving me sort of 0.9, 0.99, 0.98 here. It's a very high performance on this set. Now, this, when you have these scores, as you'll see here, I have to find a threshold where I cut them and say anything above the score is a positive and anything below the score is a negative. And that's a decision I get to make as the model developer. I've got a very simple script here that's just trying to say, I want to maximize the sum of sensitivity and specificity. Now, you can have a different trade-off. It depends what you want, but that's just a very simple metric. And using that, I get 0.67. And the sensitivity there is 92% and specificity 96%. Now, does it differ by tissue type? I expect it does. I don't have information on the tissue types. I think it's actually all one tissue type on the Chameleon data set. Could be wrong on that. But you can obviously run that experiment and look at it if you have other tissue types you want to run this on. So that's the opportunity there. But it wouldn't surprise me if there was a difference between tissue types. I think that's to be expected, especially if the training set is not balanced for different tissue types, right? Like if you have a concentration of a particular tissue type, then the model will learn that better than it will learn ones that are less represented.
And then I have a little bit more of a philosophical question with regard to how I guess it's more of a mathematics question. It doesn't matter. The question is, you are feeding this patches of positive for tumor, negative for tumor, false positive for tumor, false negative for tumor, around a specific tumor. So you're feeding it hundreds or thousands of slides of the same kind of tumor from the same tissue and saying, this is normal, this is not normal, this not normal is cancer, this not normal is a false positive, et cetera. And it's a compare contrast kind of algorithm where you're asking it to learn by comparison. What would happen, or how would you structure it differently if you wanted to feed it all normal tissue, but teach it to recognize what that tissue was? Like, so let's say you wanted to feed it, 100 sections of lung, 100 sections of normal breast, 100 sections, but and the outcome is you wanted the AI output to be, this is lung tissue, this is breast tissue. I mean, you may have already done that, but is it the same tool, or is it a different way you would have to approach that? Because you would want an all for one. You give it an image and then it tells you the tissue. How would that work?
Absolutely, great question. And there's a couple ways to do this. The way I would do it, which is maybe a little less exciting, but hopefully easy to understand, is I'd actually build a separate lung classifier, breast classifier, cervical classifier, prostate classifier. So you'd have these linear probes, because they're very cheap to run. That, as we said, it's a very simple operation. You can have and train, like you put all your prostate patches in there and say, this is a positive label now, and then all my other stuff is a negative label. So it learns to distinguish prostate versus not prostate. And you do the same for lung, you do the same for breast, you do the same for that. And then when you run them, you actually run all, let's say, whatever, 6 models in concert. And you say, which is the highest score? That's the one that I think it is. So that's the way you do that. Now, there's other ways to do that in machine learning. You can have what's called a multi-head prediction, where you actually have, you sort of feed it multiple heads. We tend to like to binarize things, but obviously that's just a decision you get to make. But in terms of that, we'd probably just do that and then present it as you get a different answer. So it's not just a binary, but under the hood actually it's binaries, and we just max the maximum score.
Yeah, the reason I asked that question is because, and this is the philosophical part of it. Part of the problem that our industry colleagues are having who are trying to commercialize AI, even especially in the pathology space, but really anywhere, but certainly in the pathology space, part of the challenge is the business model, right? Because if you are a general pathology lab, like all of our participants today are going to come from general pathology labs, you have, your first slide's of lungs, next slide's of breast, third slide's of prostate, fourth slide's of lung, fifth slide's of colon. And, to truly change the way that someone's practice, to be disruptive to their practice, you have to think about what does their workflow look like and how could AI really affect that. And what I think is, my histotechs receive all of the tissue, they process it, they make slides, they scan everything, and then I sit down to my workstation and case number 1 comes up and the AI has already said, oh, this is a lung case, not because somebody told me, but because I looked at the tissue and this is a lung case, and I've gone and pulled the lung algorithm from company X's website or cloud or wherever, and I've run it, and here's the annotation. And then the next case is colon. Oh, I've gone and called company B's. And why is that important? Because it creates a meta tool, which you can have a business model for. And that meta tool can now have a commercial relationship with all of those algorithms. And the individual pathology lab isn't having to buy 40 algorithms, right? Or subscribe to 40 algorithms. And I think no one thinks one company is going to develop every algorithm, right? One company is going to develop several, another company is going to develop several. There are just too many cancers. There's 2,000 cancers out there. But if there was a meta approach where, not to use the word meta in that way, but there was if there was a different approach so that the whole slide image, prior to the pathologist even look at it, the whole slide image could be said, okay, this is lung, here are the available algorithms. So that when they sit down, it says, this is a lung case, here are 3 lung algorithms that are available through this platform. Which one would you like to run? Or we suggest you run the cancer one, or it's already run it and said, here's the, I just feel like the business problem of AI in pathology is, nitpicky subscriptions times 25 to try to get your work done. But the real business solution is a tool that can recognize any tissue and say, here's the model you need, right? And I just think someone like Google is the right team to be able to think about it, again, pardon the pun, from a meta point of view and say, okay, this is we can build this algorithm, we can feed all this tissue in, and then all the other 25, 35, 400, whatever it is, AI companies can use this tool. They can work through this tool to actually have it available to pathologists. That's where I think the true disruptive innovation and true change to the field of practice for pathology will happen. Because at the moment, part of the problem, your AI is open access. People can use it. It doesn't cost anything except time, which is very expensive, but it isn't costing their organization necessarily money to do that. But commercial AIs are saying, oh, pay us a $20,000 subscription or pay us a per click subscription to do that. And then it's like, which one do you pick? It's like, oh, am I really having that much trouble with breasts? Does it take me that much time? It's not a huge volume. So I don't think it's a really good value. Plus you have to convince the CFO, as opposed to if someone says, oh, I'm gonna subscribe to, or I'm gonna buy, you know, UberPath or whatever clever name it came up with, and now all of my whole site images are fed into it, and then I get a menu of options for AIs that I could choose from, which already have a relationship with Uber AI that I don't need to worry about. They're getting paid somewhere else, and I just use my Uber AI to pull down my algorithm and get the right result. That is just like a vision I have for how this could work. And as you said, your binary systems of 6 different models underneath can do that, but if you spend your time building one really good binary system and then have a third-party program that can say, yeah, let's pull this one in, I think it's more effective and more efficient. That's just my opinion.
Yeah, no, that's a great thought. And you know, we're just at the beginning of this. This was released a couple of weeks ago, so I think it's very possible to build that kind of system. And in radiology, we have actually very similar. My friends at Google Cloud have built this for some other clients where they've said we've got like 10 vendors. We need to know, because it costs us money every time we run this. I don't want to run my lung CT model on an incidental chest CT. I want to run it on my cancer screening model. I don't want to spend the money for that. It's not worth it for me. So I want to know what's the right study to send this to, because otherwise I'm paying per click, and that's expensive, right? So I need to be quite judicious about when I run this. In terms of the tissue classification, you know, that's something that what we hope at Google is, as people build these things, they can actually share the linear classifiers, and then you could share it with your lab down the road or colleague, and they can run the same thing and it'll work, right? They can generate the same embeddings, recognize them the same way. So if somebody was to build a lung cancer classifier, a lung tissue classifier, you could just share that and say, here's the weights, that there's 384 numbers, and this will convert my embedding into a lung tissue identification. So there's a potential collaboration there. I mean, it can be academic, it could be commercial if someone wanted to license that, but that's something that is available with this system. And you know, we've got to build the pipes to make that possible, but that's the direction we're thinking about. How do we enable the entire ecosystem to like allow people to do these things together? But I'll just say one thing about the embeddings, if I can, which is, you know, you had your example where it's lung tissue. Okay, I'm going to send it now to my lung tissue AI, my suite of AIs that run on lung tissue. The beautiful thing about the embeddings is that if you do have your own lung tissue AI, you actually can call that linear probe, and that's a very simple compute operation because you've already got the embeddings, right? So the first step is to take these embeddings and say, is this lung tissue? Okay, yes, it is. And now I'm going to send it to my 5 other linear probes that do lung cancer specific things or lung tissue specific things. And you don't have to run the compute twice. So it's much cheaper for you and much faster because you've already done the hard work at the outset. And that's the important thing to realize is, like, once you've got the embeddings, you can power, you know, a huge amount of applications from that very, very efficiently, very cheaply from a compute perspective and from a time perspective.
Yeah. And I think, you know, and I apologize, I have to get on another call. But I think that one of the things that we're used to in the laboratory is interfacing, right? The whole concept that like our instruments are bound into our LIS, et cetera. And so the clinical pathology side of the world understands this whole kind of the network of the lab and all this stuff being integrated and the answers coming from multiple directions and being pushed into the LIS. And I think AP, anatomic pathology, hasn't had that luxury, right? It's all a lot of wet work and people doing a lot of things, and then they go and they put just in a report at the same time. But when you think about all of the cloud-based AI and all these other tools being out there, we really have to envision pathology as that network of the laboratory and pulling in the data. So it's really the way to go forward, I think, for the lab.
Absolutely, yeah. Look, we're hoping to see how this tool gets received and encourage people to use it. And as we go, we have the opportunity to build this out and make it a more holistic experience. Right now, it's a research tool, but there's obviously opportunity with our partnership with Google Cloud to make this a more end-to-end solution.
Yeah. Well, thank you so much, Rory. I think what we can do is close it out here, and we will share the recording with our colleagues, and I'm sure there will be more questions. Certainly, I'm sure people will reach out and ask for additional demos or help if they're trying to work with it. So thank you again so much for this presentation. We really appreciate you taking the time today and the early hour. to do it. And we look forward to working with you again.
Absolutely. And I'll send through some of the materials because there's a few links I promised to share. So I'll send those through. Dan, best person to send to you?
Sure. And then we can connect them to the recording.
Fantastic. All right.
Okay.
Look, everyone, thanks for the opportunity. Really appreciate it.
Thank you. All right. Bye-bye.